So we're going to look at some examples and infinite series, and these examples they involve the application of the integral test. Okay, so the question that we have reads: verify that the integral test can be applied to the following series, and use it to determine convergence or divergence. So we have been given these three series A, B, and C. Okay, so we have to determine whether they are convergent, whether they converge or they diverge, and what we are applying is the integral test. But before we do that, we have been the question is asking us to verify. Okay, so you might want to say, what does it really mean for me to verify? It's about understanding what the integral test is all about. So before doing anything, let me just give a brief summary, kind of like what the integral test is all about. Okay, so when it comes to the integral test, we say if let's say if f, of course, a function, if f is positive, okay, if f is positive, um, continuous, okay, if it is positive, continuous, and decreasing, okay, and decreasing for x greater than or equal to positive 1. um, so if you have a function f that is positive, so you can actually take this series and write it as a function. So that's what we mean. So if it is positive, continuous, and decreasing for this right here, for this interval that we have been given, then we can apply the integral test. So what what does it follow after we have confirmed that it's positive, continuous, and decreasing for that interval? We say then the series a sub n is equals to f of n, okay, of which actually in place of n you can actually use x. There's no harm. Okay, so if these three are satisfied right here, then your series a sub n is equals to f of n. Okay, so that's kind of like the interesting part about this. That's where everything starts to become clear. So what it simply means is that your series, okay, your series, you have your infinite sum here from n is equals to 1, let's say, to positive infinity of your series a sub n, and and the integral from 1 to positive infinity of f of x dx. So these three being satisfied, okay, then your a sub n is equals to f of n. Okay, so let me just try to write this a bit properly. Maybe to someone it looks like e. Okay, that's f of n, like that. Then your series a sub n and these either both diverge or converge. So what I'm trying to do is that I'm trying to run away from me using something that is complicated, something that is given in terms of this series. I'm trying to use this format that would be very much easier for me to determine um, its convergence or divergence. But again, it's not just about determining if it converges. Let's say, for example, you determine if it converges. The big deal is about what does it converge to. You should keep that in mind. Okay, so it's not just a matter of, okay, it converges, it diverges. What value does it converge to, or what expression? But it's usually a value anyway. So this is the idea. Is it positive? Is it continuous? Is it decreasing for this interval? After that, then it's quite obvious, or we're going to write it to say your a sub n is equals to your f of n. Then this being true, it simply means this and that either both converge or diverge. If this one converges, meaning the same applies to that one. So instead of me using a sub n, it's interesting that I can actually use this one. So whatever happens to this one is the same thing that happened to that one there. So that's how interesting this is. And again, remember, if you are determining if it's convergent, so try to determine what it converges to. Okay, so let's go ahead and look at the first example. So before even doing anything, I can actually tell you to say this is continuous and it's positive. You can actually look at it from this graph right here. I tried to check it out on a graphing calculator. I don't know why, but I felt lazy try to graph it on my own, so I just kind of like used a graphing calculator. Okay, which is this one right here. That was the result. So it's actually positive. So a function being positive, meaning it's like on the positive part of the y-axis. So here's what I'm talking about. If you have something like this, so if a function is on this part, meaning it's positive. If it's down here, meaning it's negative. That's what we mean by it being positive. That's what you need to verify. So it's positive, as you can see. It is continuous and it's also decreasing. You can actually try the others as well, in terms of a graph. Okay, a graph actually gives you a clear picture of how everything is. Okay, so now let's try to look at each of these examples. We try to determine if it converges or diverges. But before we do that, take this time to subscribe if you're not subscribed to the channel. We have a lot of exciting content that is coming up, so that you don't miss out on any upload. Ensure you subscribe, ring the notification bell. Okay, all right. So having said that your a sub n is equals to your f of n, okay, your f of n, which I can actually write as f of x. Okay, this is equals to my a over, sorry, my 1 over x ln of x squared. So I don't want to use n. You can use n, it's fine, but preferably use x. Okay, so what we'll do right here is to evaluate this integral from positive 1 to infinity. Wait a minute, this is actually from positive 2. Okay, that could have costed me a little bit. So that is from positive 2 to infinity. So we have 1 over x by ln of x uh, squared dx, like that. Okay, so now it's just a matter of integrating. So whatever method works well for you in terms of integration, you can go ahead and use it, as long as you get the integral that you're looking for. But that method needs to be needs to save your time, of course. Okay, so what I'm going to do is that I'm going to try to use I'm going to let u be equals to ln of x. Okay, just ln of x. Okay, ln of x, meaning my du will be equals to 1 over x. I'm using new substitution here. I'm trying to cancel out this x here, so that would be du dx, meaning dx is equals to x du. Okay, so I can come back here and say we have 2 to infinity, then that is 1 over, that is x, then that will be u squared, because I said ln of x is equals to u. Then I'll put, instead of dx here, I'm going to put what dx is, and it's actually x by du. So you observe that this and that is able to cancel out. Then we remain with that. So that is actually, we can write this as u to the minus 2. Instead of writing it on the denominator, I can take it up on the numerator to be the numerator, then du. So you can actually go ahead and integrate this, and you observe that this is just going to this is going to be minus u to the minus 1. But instead of me writing like that, I can write it as 1 over u, like that. Then evaluating from positive 2 to positive infinity. Okay, so what can I do? Remember, we have said our u is equals to ln of x, meaning, let me write this up here. So that will actually be minus 1 over ln of x. Interesting. Evaluating from positive 2 to infinity. Then you can go ahead and say, okay, I can now do the substitution and say 1 over natural log of infinity minus but that's going to be plus. Why am I saying plus? I'm supposed to say minus, but because of this minus, meaning you're going to multiply and that's going to give you positive. I believe by now we all know how that works. So this is actually ln of 2, like that. Then this gives you a 0. Why is it a 0? Okay, it's not really like a 0, but it gives you a 0 somehow. But because the number of the denominator gets like it's very very big, then you're getting a smaller number divided by a way bigger number. So it's more like you're saying 0.00000 some, like there are a lot of decimal places which are zeros, meaning you can just write it as a 0. So in other words, we can find we were able to like confidently say there are a lot of ways to write a 0. You can write it 0 as 0.00. Let's say you put 100 zeros, then you put 1, that's still a 0. Yeah, so it's for this one, the answer that we get is 1 over natural log of 2. So uh, what have I, or what have we together found out here? So we have found out to say this one here, the integral uh, from positive 2 to infinity of 1 over x ln of x squared dx, we have found that is equals to 1 over uh, ln of 2. So of which this converges. Okay, we can write to say it converges, and it converges to what? It converges to this value that we have found here, that value that we have found there. So uh, this being what we have found, therefore I can actually write it to say, I'll say because, that's how I write, that's a shortcut for because that is equals to that, therefore um, that series there, uh, ln of n squared, I'll say it converges to, just erase this, you can write to say it converges to 1 over natural log of 2, and that's the solution, like that. That's how you present the solution. Is much, yeah. Okay, so let's look at the second example. So one thing that we have observed is just a matter of knowing how to integrate. It's as simple as that. You integrate, you evaluate, look at what you get, but of course we should not be forgetting to verify. But you can actually try to verify these two, graph them if you like, then see if it's continuous, positive, and it's decreasing for x greater than or equal to 1. Okay, so now for the second one, we're evaluating the integral from positive 1, actually, from, I mean, to infinity. So this would be arctan n, but keep in mind when someone says arctan, or when you write arctan is the same as tan inverse. So if you see tan inverse somewhere else, don't think it's different. Arctan and tan inverse are the same. So instead of me using arctan, let me write it as tan inverse of n, but in this case I'll use x, divide by x squared plus 1 dx. Okay, so what do I do? Once again, it's just a matter of what method of integration works well for you. It's from this point, it's actually up to you. You are at liberty to use whatever method that you want to use, as long as that method saves your time and it's kind of like, let me just say, it's efficient. Okay, so what I'm going to do is I'm going to use your substitution again. So I'll say u is let u be equals to my tan inverse of x. Then you observe that my du dx will be equals to 1 over x squared plus 1. So when I just have to make my dx the sub of the formula so that I come back and substitute here. And someone might wonder, say, wait a minute, how have you found this one here? Like, how has it come about? I think we've been doing this for a long time now. Yeah, I think it just remains up there. Like when you do these examples a lot, like it just remains up there. And the more you practice these things, the more you're going to be seeing some answer. You don't have to actually try to write it down. You can actually see it. Okay, I think this one is, yeah. So it's because you have worked around them for a long time. So how I come up with this one, for the sake of that one individual who is like how, okay, here's how. Let me give you y is equals to uh, tan inverse of x. Okay, I want to try to differentiate that one there because that's basically what I did. I just had to differentiate. So how do you differentiate? So this here, for convenience's sake, I want to try to find dy dx. For convenience's sake, I'm going to write it as x is equals to tan y. Wait, this is interesting. It has changed from being inverse to just being tan, but this and that are one and the same thing. That's the most interesting part. So one thing that I would do right here is that instead of me finding what you usually find, which is dy dx, I'm going to have to find dx dy. So that would be dx dy. It's like we are looking for the inverse. This right here is the inverse of this inverse. Can you imagine how interesting it is? Like you have the inverse of the inverse. Okay, so the derivative of this one here is nothing but sec squared y. Okay, sec squared y, and we know that sec theta is same as 1 over cos theta, so I can write this as 1 over cos squared y. All right, so now we were looking for dy dx. Now we have dx dy. What do we do? Just swap, like swap them. So this would be like dy dx, meaning even this side, instead of having 1 over cos squared y, that would be just cos squared y divided by 1. You don't have to put the 1. Then have we gotten the solution? Not yet. So just look at this right angle triangle here, like that. Then you have a y here. That's your angle. Why am I talking about it being the angle? I'm picking it from the inverse of the inverse, as I call it. Yeah, so tan y is equals to x. Remember from SOHCAHTOA, tan theta is equals to opposite over adjacent, and my opposite is x, meaning adjacent might be 1. Actually it is 1. So your opposite is x, your adjacent is 1, meaning the hypotenuse must be the square root of x squared plus 1. So what you do is that you come here and say, okay, cos y. What is cos y? From SOHCAHTOA, we know what cos is. So we say cos theta. Theta is our angle, in this case is y. It's actually 1 over, it's 1 over, no. Cos theta is adjacent over hypotenuse. Your adjacent is 1, your hypotenuse is the square root of x squared plus 1. So we're going to say open bracket, since it's squared, it's 1 over the square root of x squared plus 1 squared. So when you distribute the squared in like with everything that you have inside there, you're going to end up with 1 over x squared plus 1. That's how I'm getting that one. I believe it's clear now to that one individual who was asking how. That's how we get it. Okay, so now I'll come here and say, evaluating from 1 to positive infinity, instead of tan inverse, I'm going to put u divided by x squared plus 1. Instead of dx, I'm going to put, like you have to make dx the sub of the formula from that one. You observe that your dx will be equals to x squared plus 1 du. So that would be x squared plus 1 du. Very interesting. That goes and that goes. I don't know why, but I just love it when I see things cancelling out in math, because I see and I understand that I'm getting closer to my answer, because it's cancelling out something, it simplifies things actually. So this is what we now end up with. So we are still evaluating from 1 to positive infinity, that is u du. Integrating that, what do we get? We actually get u squared divided by 2. Okay, so now here's what you do. You have another choice to make. Do you like write u in terms of what you had at first, or just like you just um or you just change, look at what the units really are. It's actually up to you. Either ways, it's still going to work out. Okay, so remember to say, we said u is equals to tan inverse. So now for this one I can say that would be tan. I can actually just write it as tan inverse of x, like that, divide by 2. So from 1 to, oh, squared, like that, 1 to infinity. What is this equals to? So I'll say tan inverse of infinity, like that, squared. Let me just put 1 over 2 outside, like this 2. Then I'll say minus, I'll say again, open bracket, tan inverse of 1, then I'll say squared. What is this equals to? That would be 1 over 2 outside. So tan inverse of 90, sorry, tan inverse of infinity is actually 90, which is pi over 2. But instead of just saying pi over 2, remember there's this square, so that would be like pi squared over, that would be pi squared over 4, like that. Okay, over 4, because it's supposed to be 90, so it's supposed to be like pi squared over, sorry, it's supposed to be pi over 2, then you square it, then obviously it gives you that one there. Okay, then for the other one we say minus, it's tan inverse of 1 is 45. Okay, so it's 45 squared. In terms of radians, I don't use radians. It's pi over 4, but that would be pi squared over 16. Okay, so this would be equals to 1 over 2. Then that would be, you can write this as a single fraction, and it will actually be something like 3 pi squared over 16, which ends up to be 3 pi squared over 32. What does this tell us? Okay, so you can actually write the conclusion here. Once again, we'll say because that we say it was tan inverse or arctan anyways, so that would be x divided by x squared plus 1, if that is dx, if this is equals to 3 pi squared over 32. Therefore therefore the series a sub n, which is written as infinite sum from n is equals to 1 arctan n divided by n squared plus 1, it converges to this value here that we have found, this one here. Okay, so yeah, that's how we come up with that one. Let's look at the last example. So for the last example, this is actually pretty straightforward. So for the last example, we have from 1 to infinity. So instead of n, I'll use x divided by x to the 4th plus 1 dx. For simplicity purposes, allow me to make some manipulation here. That would be like 1 to infinity. So I'll still put x divide by, so here I'll put x squared, x squared plus 1 dx. I'm just using this for me to, so that it will be much easier for me to when I'm integrating this. So this means I can let my u be equals to x squared, okay, which is this one that's inside there. Okay, so my du will be equals to 2x dx, meaning dx is equals to du over 2x. Okay, so for this one I have like x divided by u squared plus 1 multiplied by what's my dx. Dx is du over 2x. That can cancel out with that one, so I have like 1 over 2 from 1 to positive infinity, 1 over u squared plus 1 du. Okay, I believe you remember to say when we differentiated this one we got something of that format, meaning when you integrate this one you get back to that one. I'm not talking about question B, I'm talking about question C, but I'm looking at what I got, so it's just kind of like making reference to the past. Okay, so this is simply equals to 1 over 2. This is going to be inverse tan inverse of u. Okay, uh, evaluating from 1 to positive infinity. Okay, so once again here I have a choice to make. I can actually evaluate it in terms of u or in terms of x. It's up to me. I'm not restricted. Okay, so what I would do is that for simplicity purposes, let me just evaluate it in terms of u. So remember we said uh, we let our u be equals to x squared. So let's try to find out what u is in terms of x. So it's actually the same. If you plug in infinity here, this will still be infinity. If you plug in 1 here, this will still be equals to 1. So we are actually going to say it's 1 over 2. 1 over 2 is the same. So you can say it's tan inverse of u, in this case, which is infinity, minus, that's the upper limit, then tan inverse of 1, which is the lower limit, and this will be equals to 1 over 2. So we say tan inverse of infinity is 90, which is pi over 2 minus pi over 4. Okay, so this is 1 over 2, so that would be 2 pi, that is 2 pi minus pi divided by 4. We get something like pi over 8. That's what we get. So we can say because the integral from 1 to positive infinity of x over x to the fourth plus 1 dx has given us pi over 8. Therefore, the infinite sum from n is equals to 1 to infinity of n divided by n to the fourth plus 1 converges to pi over 8. That's what we get right there. So this is basically how you look at these questions. It's just a matter of knowing how to integrate and understanding how you maneuver around the integral test, the verifying, and the like. So that's all in this video. Thank you very much for watching, and we'll catch you in the next one.